Welcome to Q&A Wire.
We want to calculate what would be the enthalpy corresponding for Cr2O3 for chromium oxide at 1900 degrees Celsius, given the information that the delta H standard at 298 would be equal to minus 112,968 joules per mole, and we know that the Cp is going to have a temperature dependence as 119.37 plus 9.2 times 10 to the minus 3 times the temperature in joule per Kelvin. So for the first part, to calculate the delta H at this temperature, what we want to do is going to be related as delta H would be equal for the integral from T1 to T2 of Cp dt. In this case, the value for delta H would correspond delta H at the second temperature, which is 1900 degrees Celsius, which is 2173 Kelvin, minus the enthalpy at 298 Kelvin, which is going to be the standard enthalpy for this compound. Put it like this. And this would be equal to the integral from 298 to 2173 Kelvin of Cp dt. So the result of doing this integration is going to give us that the enthalpy at 2173 Kelvin is going to be equal to the enthalpy at 298 Kelvin plus the result of this integral. In this case, what we're going to get is 119.37 times t, evaluated from 298 to 2173, plus 9.2 times 10 to the minus 3 over 2 t squared, evaluated over the same limits. Replacing the value over here for h at 298, which is minus 112,968 joules, the result is going to be joules plus 21,312.375 joules. All of these for 1 mole of reaction, and the final answer would be 132,163.125 joules, which corresponds to the answer of part A. And now for part B, what we need to do is calculate what is going to be the heat required and the cost of heating after a sample of this substance from 35 degrees Celsius to 920 degrees Celsius. So in this case, the temperatures would be 308.15 Kelvin all the way to 1193.15 Kelvin. So the heat required in this case is going to depend directly on the integration of the Cp over the range of temperatures of Cp dt. In this case, this is going to become the integration from 308.15 to 1193.15 of the value of Cp, which is 119.37 plus 9.2 times 10 to the minus 3 times t, all of this differential of t. And the result for this integration would give us 119.37 multiplied by the change of temperature plus 9.2 times 10 to the minus 3 over 2 multiplied by t final squared minus T initial squared. And the result is going to be in joules. The second contribution corresponds to 6,111.7923 joules. And the first contribution is going to be 7. It's going to be 105,642.45, which gives us a total heat equal to 111,754.2423 joules. And this would be the heat required. And with that, it would be all. Thank you very much, and have a good one. Before I go, just a comment over here. Notice that I changed the temperatures to Kelvin. Over here, this is because we're not only going to have a value for delta T, we're also going to have a T squared contribution after we have done the integration, right? So in this case, this is why it is important to convert from Celsius to Kelvin. And with that, it will be all. Thanks and have a good one.